Hi, sir.
Hi, Amy. How are you doing?
I'm all right, thank you. How are you?
Good. Good. Very good. Yes. So, are you practicing some questions with integration?
Yeah, I've done a few questions from my book and things. So, yeah,
That's very good.
all okay so yeah.
That's very good. So, no difficulty, right?
No, not yet.
That's very good. That's very good. So, it's a actually complicated unit, and we need to go back and forth with derivatives. So, today I'll actually discuss with you about fundamental theorem of calculus. That is very basic. And very important, I shouldn't say very basic, most important. It really connects the derivatives with the integrals and the basic concept of calculus, right? Uh,
Mm.
for that, we should really give a lot of credit to Cambridge University. You're trying for that. And, there have been stalwarts from there, especially Newton, his teacher, and following him, so many other people who have contributed a lot in this particular area. So we'll see how they really changed mathematics and looking into the real life situation and modeling them in a very different ways, right? That is what we are going to see today. So let me share with you the screen. Created this particular video for you. So what we have here is, as you can see, fundamental theorem of calculus, right? That is what we'll talk about today. Today we are going to discuss fundamental theorem of calculus, and we'll talk about these topics. Right there on your screen, you can see derivatives of area and functions, area under the curve, fundamental theorem of calculus part 1, definite integral concept, fundamental theorem of calculus part 2, and we'll take up velocity displacement applications. Correct? Sounds good? Now,
Sounds good.
very good. Now, I saw your curriculum about GCSE level A in your part 1, year 12. Fundamental theorem is not included. However, moving forward, I thought it important to introduce it right now because later you're going to use it, right? Next year you're going to use it. So it's a good idea to do it now and then move forward. So that is why I'm taking it in between. So let's talk about area under the curve to begin with. So here is a simple example. Most of my examples are very simple. The idea is to understand the concept. So example here is find the area of shaded region under the curve of f of x equals to 2x plus 1. 2x plus 1 is the straight line which is shown here on the graph. Area is bounded by the vertical line x equals to 1 and the moving boundary x equals to x. I'll tell you what moving boundary really means. Above the x-axis and below the line. So we're talking about the area which is bounded on the top with the line itself. On the sides, the vertical lines is x equals to 1 and x equals to x. At the bottom, it is the x-axis. So basically, we are saying we're looking at a part of the graph which is positive, right? Area, is a positive thing. To keep things simple, we have taken a portion of the graph which is positive. Okay. Now, this part is kind of tricky to understand when we say x equals to x and we are saying moving boundary. We really mean our initial point is set at x equals to 1, but this point is moving. We are actually moving this point left or right. You can see if I move it left, the area decreases. And if I move it right, the area increases, correct? So as I move, the area really depends on the position of x, correct? If I go further right, area increases, correct? So that is how it is. So that is the moving boundary. We'll get to this understanding as we move along. Now to find the area under this curve, very simple, it's the trapezoid. So you know the formula, which is half of, you can add the parallel sides and multiply by the distance between them. So that becomes the area of this particular shaded region. So what I did was half of, when you want to add these side lengths, these are actually the y values, correct? At x equals to 1 and x equals to x. So f of 1 and f of x gives you that y value. And the distance between them is the difference between x and 1. So that is how you get x and 1, correct? So that is the difference between these two. So is this formula clear and how it is applied?
Yeah, makes sense.
Okay. Now, if I substitute 1 in the equation of the line, which is f of 2x plus 1, I get this value. So substituting 1, I get in this particular thing, well, we get 2 plus 1, which is 3, right? So let me just highlight this. So this 1 is 3. So if I substitute 1 here, we get 2 plus 1, which is 3, correct? And f of x as such is all this. Is that clear? So 2x plus 1 is f of x, and f of 1 is 3. So I wrote 3 for f of 1, and then 2x plus 1 is f of x, and then we'll multiply this with x minus 1. So you can simplify this expression. You get 4 plus 2x times x minus 1. When you do this distributive property, you can combine the like terms and write down the expression as 2x squared plus 2x minus 4. Half of that is x squared plus x minus 2. So ultimately, we get the area under the curve. So that becomes the area under this particular curve. So is this clear to you, Amy, up to this place?
Yeah, yeah.
Good. Now, you will notice one thing which was observed, and that creates a lot of simplicity for finding area under the curves. And that is, if I do derivative of this, x squared plus x minus 2, what do I get? So, yes.
Oh, no. Was that a question?
Yes.
So, derivative of x squared plus x minus 2 would be 2x plus 1, and the minus 2 would just be 0.
0. So 2x plus 1 is the function itself. Do you see that? So the area derivative is the same as the function. That is the observation.
Oh.
Got it?
Yeah.
So we wrote here that the derivative of this area, which is right there, is d dx of x squared plus x minus 2, which is 2x plus 1, which is the function itself. So here we get a differential equation. Do you see that?
Oh.
X is f of x, and we can solve this taking integrals on both the sides. So that is how you see the derivative part and the integral part and the area part being related. So area under a curve can be easily found by integrating the given function itself in a boundary, because area always will have a boundary, correct? So this is the concept of area relation between the derivative and the integral, right? That's a huge connection. So in a way, we connected gradients with the area under the curve with this particular equation. Clear?
Yeah.
We'll see it in a general case. We took a very simple case, a straight line, and became very easy for us to do all that. Well, let's take a general case. Now, in this general case, example 2, we'll have find the area of shaded regions shown under the curve y equals to f of x, where P and R are extremely close. So we're just taking any 2 points which are very close and a general function f of x, right? So we've taken P and R as 2 points. Any function f of x, not a straight line necessarily. Okay. In that case, since these 2 points are very close, I'm assuming them to be just delta x away. Delta x means very, very small, right? So the x value of P is x, the x value of R is x plus delta x. The y value of P is y, the y value of R is y plus delta y. That is this much extra, correct? It is on the right hand side. Now, if we try to figure out the area of the shaded region, which is like shaded in right there, then this area is between 2 values. And the 2 values, as you can see, are 2 rectangles. One is the small rectangle, and which is this one, correct? The smaller rectangle. So the smaller rectangle side is dx and the length is y. So we can multiply dx and y. It is definitely more than this. On the other hand, we have a bigger rectangle where we have additional length of delta y. So y plus delta y times dx is more than the required area. So definitely, this area is between these two values, right? Now, important thing here is that we have the upper and the lower bound of this area, correct? Let me just divide both sides by delta x. So if I divide by delta x, these delta x cancel, and we get y is less than, delta y delta x is greater than y, but less than y plus delta y. Now, since we know that delta x is approaching 0, delta y will also be very small. So basically, we get this delta A over delta x, that small change in area with movement along the x-axis can be written as dA dx. That is what derivative is. Secant changes to tangent, right? For very, very close points. So we have dA over dx right there. And this value is squeezed between the y values because delta y is also very small. So what we notice is that dA dx will approach y because we are approaching y from the right side. The left side value is y. So dA over dx is y, and y is the function. So we again came to the same important relation, which is dA dx, rate of change of area, is equal to the function itself. Does it make sense?
Oh, right, yeah. So with the question before that, when we saw the derivative being equal to the rate of change of the area being equal
Yes.
to the function, is
Yes.
that what you mean, basically?
Yes.
Oh, okay.
So whether you take a straight line or you take any general case, we get the same result.
Oh,
Correct?
oh, okay.
Exactly the same result.
Mm.
That means that the derivative of the area is the function itself. It's a differential equation. You got a derivative of one side,
Oh,
right? A function on the other side. You can integrate antiderivatives to get the area itself. See how simple it has become? Finding area under the curve, so difficult. And now we have a very
yeah.
simple way. Antiderivative of the function is the area under the curve.
Oh, yeah, makes sense.
Yeah, right. Another important thing here will be this moving boundary. If I move more, area increases. If I move less, area decreases. And if I overlap with the initial point, it is 0 because then the width is 0.
No.
So it is
Yeah.
that.
And you can't go past the point because
Yeah.
you can't have negative area, can you?
So you have to have a lower bound and an upper bound, right? The upper bound could be as close to the lower bound, but could be farther away. Depends on how much area you want to consider. Is that okay?
Right. Yeah.
This leads to the fundamental theorem of calculus part 1. This fundamental theorem is actually in 2 parts, and this is what the first part is, that the rate of change of area is related with the function itself. And to put it in words, it could be said like this: if f is continuous, f has to be continuous function within the two closed interval, right, including both a and b, then the function f of x is integral of that because it was antiderivative. We can integrate it into area, right? So f of x is
Right.
a to x of f of t d of t, where a and b are your closed intervals, right? So x is in anywhere in between a and b. Second, it is continuous within a and b, and it is also differentiable in the open interval of a and b, right? So the key idea here is we can now find the integral. We know it is antiderivative of the function.
Oh, okay. Yeah.
Correct? So this is your part 1, which really tells you how to find the integral, how to connect this particular integral with the derivatives which you have done. So it connects the two problems, one of gradient and the other one of finding area under the curve. Correct?
Oh, okay. Yeah.
Note, if f is positive function, then capital F of x can be interpreted as area under the graph of f from a to x, where x can vary from a to b as shown in the example 2, right? It has to be a positive function. Even otherwise, you get the derivative and the integrals, but integral will not be area, right? It has a negative value. So that's kind of important to understand. So let's move forward with the same concept and take up some example. So example number 3 is find area of the shaded region shown under the graph on the curve y equals to 3x to the power of 5 plus 3 between x equals to minus 1 and 2. So here is the graph for that. These are the two limits, x equals to 1 and x equals to 2. So what we are doing actually to find the area, we take anywhere in between a point and we say let x be equal to x. So it is from minus 1 to x. And then we change x to the upper bound of 2. Perfect. And so that is how we actually work it out. Okay. So let A be the shaded region which is bounded by the curve, the x-axis, and the moving boundary PQ. Then we have seen that dA dx is equal to y itself, and the function is 3x to the power of 5 plus 3. To solve this, we have to integrate both sides. When you integrate, you get A on the left-hand side, and on the right-hand side, we get half of x to the power of 6 plus 3x plus c, right? Now, when x is minus 1, A is 0. So when you are at this particular boundary on the left side, right, it just collapses and the area is 0. So if you substitute that value, then you get c value of 5 by 2, correct? Now, you can substitute the value of 5 by 2 and you get your area function, which is right there. And in this area function, if I write x equals to 2, which is my outer boundary, upper bound, in that case, I get the total area, which is 40.5. So we used our basic principles, which we had been doing antiderivatives, just to show that it really works with this example also, right? Now, what you could do directly is you could integrate 3x to the power of 5 plus 3 using your antiderivatives and take a limit from minus 1 and 2 to get the answer. Then also you'll get the same answer, right? That's the whole thing. So we'll do that process in our next example. Okay. So the next example here is we are now find the area of the shaded region under the curve y equals to f of x between the curve and the x-axis and the line x equals to a and x equals to b. Now we have taken a general case this time. We have a function f of x. These are the two boundaries, x equals to a and x equals to b. That is the x-axis. So what we are doing now is that we are extending the concept which we learned from Newton's first observation, and we are moving forward to find another way of finding the integral. So last time what you observed is that c value could have been cancelled if you're talking about two boundaries, and that is being shown in example 4. Okay, so we have a function y equals to f of x, and we learned that area is basically equal to the function itself, the antiderivative, plus c, right? That is what area is, as we saw last time. Now, when x equals to a, area is 0. At this particular point, area is particularly 0. So we get the value of c as minus of fa. We are actually following the same steps which we had been doing when we used antiderivatives, right? So we are using the same steps. So we are saying that the differential equation is dA dx equals to y. When you integrate, you get antiderivative f of x, which should be equal to the area plus a constant, right? Now, boundary condition, if you're on the left bound, area is 0. So when you put area as 0, you get c as minus of f of a. So area is f of x minus f of a. Now, you put x equals to b. When you put x equals to b, you get f of b minus f of a. So what is area equals to? Area basically is difference of these two values. So basically what we are trying to say now is we understood that area is integral of the function within the given boundaries a and b, and now we have understood a method of finding its value. Its value is antiderivative b minus antiderivative at x equals to a. That gives you the value. And this is the second part of fundamental theorem of calculus. This can also be written as f of x with lower boundary a and the upper boundary b. You get the idea. We got a method of easy calculation to find the area. And this is stated as the fundamental theorem of calculus part 2, which is if f is a continuous function on a to b, both included, then the integral f of x g of x is the value of f at b minus the value of f at a, where f is an antiderivative of the function. In other words, the derivative of the function f is function. Is that correct? Antiderivative of that area is the function. This is what we are trying to say. So part 2 of fundamental theorem tells you a way of calculating the area itself by antiderivatives value at the two intervals. Is this clear to you?
Yeah.
Correct.
So you can do it both ways.
Yes.
So you can do it the first way with the plus, like the plus c, or you can do it this way.
Correct. So this way is very, very simple.
Oh, okay.
We straight away find the antiderivative and the value at the two limits. Their difference is the answer. So it is much, much faster.
Oh, okay.
That is the whole idea, right? Now, based on this, based on this, let's take an example and see how simpler it becomes. Example 5 is utilizing what we just learned. Find the area of the shaded region shown under the curve of function 16 minus 3x squared between the curve, the x-axis, the lines x equals to 1 and x equals to 2. So those are your two boundaries. Note that it is all positive portion of the curve which we are talking about. Now we know that the function is 16 minus x squared. We know area is related and it is antiderivative. So I can find the integral of the function in the with the boundary 1 and 2. So this is the function 16 minus x squared. You can apply your power rule formulas. So you get 16x minus x cubed over 3. 3 and 3 cancel. Limits 1 to 2. That is the area. Substitute and calculate your answer. You get 9 units square as your answer. Do you see how simple the solution is?
Yeah, very simple.
That is what you do. Now we can actually deal with very complicated graphs. This simple concept. That's the whole thing, right? Let's take another example.
Right.
Yeah, let's take another example. We did kinematics, we did velocity. Same type of question. How are we going to do now? Question is, velocity of an object is given by the function v of x equals to 16 minus 3x squared. Determine the distance traveled by the object in the interval 1 to 2, both included. Now, you know velocity is rate of change of displacement, right? So that means velocity is rate of change s prime x, and that gives you the idea. Antiderivative is the area. Area under the curve of velocity is distance traveled, and that is what we want to find, distance traveled. Correct? So we want the area under the velocity curve. We know that the velocity function is 16 minus 3x squared. So that means the displacement is integral of this with lower and upper bound. And you know the integral of 16 minus 3x squared is 16x minus x cubed. Again, 3 and 3 cancel. And the limits are 1 to 2. Substitute these values. Find S2 and S1. And their difference gives you the area in between, which is distance traveled. So distance is 9 units. Do you see that? So very easily, we have actually solved the same question, and what we utilized was fundamental theorem of calculus part 2. So that FB minus FA is a huge thing, and that really simplifies all the process. Do you get it?
Yeah, so much more quicker as well.
Yes.
Yeah, very effective.
Very effective way. So now I think you are open to complete concepts. Here's a very good review question.
Take a picture.
Sure.
Yes. Okay. Yeah.
This is a very interesting question. I've seen this in many test papers, and you should be ready with this question. F of x is integral 0 to x, And the function is 1 over u cube plus 1 du. X is between the boundary minus 3 to 3. So, if I put minus 3, minus cube is 27, the function is still positive, right? So we have a positive function clearly. Explain why the following statements are true. So there are 3 statements which we want to show that they are true. The very first one is f of 0 is equal to 1. So if f of x is all this, 0 is x, right? So this is x. It is equal to 1. Why it is true? See here. If I substitute x with 0, my definite integral will...
Oh, it's the same.
Correct.
Oh, yeah. So when you 0 minus 0 is just like
Zero,
there. It's
zero area.
yeah.
So that is the properties of definite integral. We know it is 0. The second one is f of minus 2 is less than 0. How do we figure this out? Well, f of minus 2 is kind of an area, right? Which we have to find of this particular function, right? So now, area is going to be positive for this function, correct? However, the limit is from 0 to minus 2, because when I change, f of minus 2 means upper bound is minus 2. Do you see that?
Right, yeah.
But you learn the properties. We can change the boundaries with a negative sign. So I made negative sign outside and boundaries from minus 2 to 0. So in the graph, I am from minus 2 to 0, negative outside. And we know this function inside is positive. Since the function is positive, it also represents the area. Area is going to be positive. Since the area is positive, but the outside we have negative, the whole thing is less than 0. So even without calculating and finding, without finding antiderivatives and things like that, we can conclude. You see that?
Yeah.
Last part. The derivative of this function at 2 is greater than 0. How do we know that? Okay. So that really means this is antiderivative, right? So the derivative of this function is the function itself. The inside part is the derivative, right? This is integral.
Oh, yeah.
F of x is the integral, right? So f prime is the function itself. And we know if I substitute 2, this is positive. So it is greater than 0. So we conclude that it is greater than 0. Otherwise, a very complicated question. But with the understanding of our rules, the properties of definite integral, and the area relation with the function, that when the function is positive, in that case, between 2 boundaries, we are looking at the area which is always positive. Correct?
Yeah.
Does that make sense? So that
makes sense. Yeah,
that brings us to the end of this class, but that opens up the chapter of finding area under the curve. Tomorrow, we will look into how to find area between 2 curves, right? So that would be our challenge, and that is kind of the last part of your learning on integration. So we'll actually conclude our session for integrations tomorrow. And I hope, so fast. So with that, write some questions from your book and then be open to try the last part and the examination style questions, okay?
Yeah.
Now, Amy, can you summarize our learnings for today?
Yeah, so we were looking at the fundamental theorem, the concepts, so part 1 and part 2. Part 1 being, so the rate of change of the area under the curve is equal to the length of, like you said, the moving boundary. So we concluded that when you do d of a over d of x, it would equal the function itself, y. And y, so the function has to be continuous and in a closed interval. So that's kind of crucial. Then towards the end, when we're looking at the different properties of it, so if the definite integral has the same limits, that means the integral would equal 0 because they're the same. And then the sign of the integral would be, there'll be a negative sign if the limits are reversed. Yeah. So that will make it less than 0. And what else? So when doing the antiderivative of, let's say, between 2 points, so B and A, by subtracting the antiderivative of B by antiderivative of A, you get the area under the curve.
Right.
Yeah.
And most important here is we are looking into a continuous function within two boundaries, and the function is positive. In tomorrow's lesson, we'll see what happens when the function is not continuous. Oh, sorry. What happens when the continuous is not positive? It is negative and positive. Even then, we can find the area. We'll take the absolute value, nothing else, right? So we can divide it into parts, add up the absolute values. They will be positive, and then we'll get the area. And that's what we are going to do tomorrow. Perfect. So with that, we close the lesson for today.
Sounds very good. Yeah.
I hope you learned. Thanks for joining in.
I learned a lot. Yeah.
Thank you. Thank you. And see you
tomorrow.
Thank
you so much, sir. Really appreciate it. Yeah, see you tomorrow. Bye.